Good afternoon. Not many people are here. Let's see who shows up. It's very blurry, isn't it? I don't want to spend too much time on the Moodle page. I just want to point out for people who seem to be a little bit lost on how to find things. Even though these sections are empty, my stuff is here. You have to just open it. They really messed up. Well, I have to say, the people who took over the Moodle messed things up by throwing this template in, and I haven't had time to delete it. So you have to click on Ver Módulos de Sección, and then you see everything. It's a mess, I have to say. Let me see how you can see everything at once. Used to be that you could see everything at once, not just the modules. I don't know what they did. But anyway, you can go between module 1 and then up here. Can you see up here? It says module 2. I'm just showing you how to navigate. Oh, you can't because it's too small. Let me see if I can shrink it. There you go. Now you should see module 2. There. So up here you can click and go to the different modules, but it bumps me up to the top again. I have to scroll down. Yeah, it's not the nicest navigator, but I think it's pretty good for storing information, better than what I've seen on for other schools. You see module 3 at the top? Let's put that down a little bit. And then I can go to the next module. So we are in unit. So this is where we are. It's unit 2 NOR, or called module 3. How confusing is that? That's just because they've separated everything by modules and I haven't erased everything. Yeah, they just changed the template, the platform for Moodle, and I have to edit it. So hopefully, I got one email asking me where to find the materials. Hopefully you found it, and I expected the past week, that you were able to finish up your review of the first part of the unit and then progress to this part of the unit. So how many of you have actually covered this material? Let me see if I can make it more visible, because it's not visible the way it is. Okay, here. There you go. So how many of you have covered this? Have you reviewed this material? So Jasmine, you have everything in just one list? That's how it should be, everything on one list. Mine seems to go module by module. I have to set something or change something. This material that's on the screen, Unit 2 NOR, was what I expected you to do this week. Unit 2 NOR. Very good, Jasmine. Anybody else able to cover this material? Great, Edgar. So essentially everything is here. All I need to do is an introduction to I wanted you to look at the histogram, and then do a little bit of NOR, And then I actually wanted to end early because I want to see the debates at 8 o'clock. So that's my agenda for today. I should ask you if you have any questions about GDS, but what I'm going to ask you to do if people are behind, I am going to ask you okay, so Edgar, don't worry, we're going to do a few problems together here for Noor. Well, you need to watch the videos with the document and, yeah. So I'll do some problems here. I will wait next week. We have, next week will be the 24th, and your test is supposed to be on next week, isn't it? What I can do next week is we can have a review. We can leave the 24th for a review, and then I can give you the test. I'm trying to think of when to give you the test. And I could postpone the test to October 1st if you want, and we can use the 24th as a review day. Because the test is going to include everything, including today's stuff. So what do you think about that? So what I'm going to do on October 1st is the first hour and a half of the class, I'll have the test, and then I'll come online for an hour to either, I don't really want to talk about that material, but I guess if you have any questions, I can cover that material, or I can move on to the regression unit. So that's what we're going to do. Hi, Freddie. All right, so I will have to put that somewhere. Sorry there's so much static. I don't know, my fan is running. My machine is older. I bought a new iPad, but it's not compatible with the computer, so now I have to get a new computer too, I think. I'll try and find a way around it, and I'll have to still use my old iPad. So, okay, so I will send everyone an email about that change. And give me a moment, I want to set up my iPad, okay? Okay, so let me see if you have any comments. No, I didn't freeze. I was just doing something. Okay. Here is, so if you ever see blurry screen, just reboot the screen. It tends to do that. So in the sample problems document, I present different sample problems. The first one I discuss in the notes and I solve the 5 features for it. The spending data we discuss in the class and we solve for the 5 features. In both of those I use the stem and leaf plot. And I think in this one I should mention, for this one I make a note that I want you to do the back-to-back stem and leaf plot for this one. You should be able to do that. You should know how to put together the data in a back-to-back stem and leaf plot. So let's do that, and then I'll go on to the third data set, which is the Newcomb data set. The other thing I want to do, okay, let me do this first, and then move on. So a back-to-back stem and leaf plot for these two, for this data set here. The question here is regarding 2 famous baseball players. Here you're given the home runs each season for their careers. Roger Maris had a career in the 60s, I believe. 60s to the 90s. No, sorry. He had a career in the 50s and 60s, and Babe Ruth, about 20 years, a generation before him. So the question becomes, look at their home run hits and comment, and then do it in a systematic way on whether, who is the better baseball player? Who is the better baseball hitter? Looking at these two, it's apparent that Babe Ruth has, regardless of it being a longer season, all his home run, all the counts of his home run in a season, most of them are higher, consistently higher than Roger Maris. So he's more consistently a higher hitter. However, in the rule books for many years, until 30 years, 40 years, almost 40 years, Roger Maris held the record for the most home runs in a season at 61. So even though the record books had him as the highest hitter, he wasn't necessarily the best baseball player. So this is sort of obvious. Most people will agree. But I use this example to illustrate how to use the 5 features and how to compare these distributions. And we begin with the graph. The graph should always have, it depends what kind of graph you want. So in this case, I want the stem and leaf plot Do I specify? Let me see what it says here, because I asked you to do it here. Back-to-back split stem and leaf plot, you see? So I'm going to refer to this. So if you have these notes, what I want to do is transfer these stem and leaf plots onto one, where they share the same stem. So the way I'm going to do that, I'm going to use, because I have to merge them and they both have different stems. This one goes by tens and this one goes by 5, intervals of 5. I was told to make a split stem and leaf, so I'm going to use this as my guide and reproduce this. And then on the flip side, actually no, I'm going to use this one with this stem going by 5s, and then I'm going to put this on the back end because that's easier to work with. Okay, so this is what I mean. I'll illustrate for you what I want you to do. So you're going to put the stem actually, I should put a title first. This is very messy, isn't it? Oh, I don't like. I do not like this application. Nope. I'm just gonna have to make it bigger. Stem. And then this will be for Maris. So messy, I don't like it. I'm gonna do this. I'm gonna write Maris leaf and Ruth leaf. And then I'm going to copy. This is 2, 2, 3, 3, 4, 4, 5, 5, and 6. That should suffice. So then I'm going to copy out Maris's. The first one was, uh-oh, what's wrong? I screwed up because I have to go higher for Maris, right? I have to go, yes. Do that again because they have to share the same stem. I'm going to run out of space. So 0, 0, those are zeros. 0, 0, 1, 1, 2, 2, 3, 3, there you go. 4, 4, 5, 5, and 6. So Maris would be 8. 8 would be here. And then 13 would be next, 3, and 14, and 16 would go into the next one. 16, right, and then we have 23, so 3 would go here, and then 26, 28, 26, 28, and then 33, 39, 33, 39, and all the way to 61. Got it? I have to make this fit. Excuse me an instant. There you go. So that's Roger Maris. It should be in a straight line. And then Babe Ruth will be on the flip side. So what you have to do is spread out 22, which would be here, and 25, and then 34, 35, this is easier because it has the same stem, 41, 41, and then 46, 46, 46, 6, 6, and 6, oh no, that's right. 6, 6, 6, 7, 9. Sorry, it's such a bad program. And then 54, 54. What happened is I accidentally erased my other software. Thought I could get a new app. It was an old app that I paid for and it just went out of service. 54, it actually crashed on me. That's why I erased it and tried to reload it. It didn't work. What was I thinking? And 60. There you go. Okay, so that is a back-to-back stem and leaf plot. I hope yours will be neater than mine. I'm gonna put bars here. Any questions? So what you see is if I was to smooth this out on the right side, either I could argue, I think that Maris's distribution is very unpredictable, seen as the high range of values, so it's volatile, spread out. It's very spread out. And we could see this as a curiosity over here, something very curious. In the tail. So this is clearly going to be seen as a right skewed distribution. On the other hand, Ruth is tight and when I draw it like that, what I'm saying, well, I'm saying relatively speaking, right? This distribution is tighter. Even though I made this look like it's like a tail, it's not a tail, right? So it'd be more smooth. I believe when I smooth this out, remember, what I'm saying is what I think the pattern would be if I had more data. Sure, it would be a longer, or it would be a deeper, you know, I go further in this direction with the distribution. But I think that it will be still the same shape. I still think that most of the values would be around this class. Some will be higher, but just as many will be lower. A few will be much higher, and just as few would be much lower. So yeah, I only have 15 observations here. If I had more, I believe that, you know, it would still have that pattern. That's what I'm saying. So this is a tighter distribution, more reliable, not volatile. That says reliable. Let me try that again. And we see this as symmetric, or I do. Now I'm telling you this because I'm going to have you compare distributions on the test. You should be able to handle that. And this is a nice way. If you're asked to make a steps back-to-back, this is a back-to-back stem and leaf plot. Notice the numbers run in this direction, this way, and then in this direction that way, okay? So it's like a mirror. And we see most of Maris's data happens before the modal class of Ruth. So on average, Ruth is going to have higher, always or consistently higher numbers than Maris is. Except for this one curious case which you need to explore for being outliers. So I recommend, if you didn't read it already, finish reading the evaluation or assessment of this problem, okay? And practice reproducing the calculations that are presented. Not left skewed because it's tight. This is not a skew. You'd have to have way more happening. Like I have all that is these two numbers and there's no gap. There's no gap. I wouldn't call this a skew. Okay? There's no gap. It's just there's, if there was more data, I think maybe there would have been more out here too. Skew is this, look at this huge gap here. That's why we call this a tail. Right tail. Okay? Yeah, you need more data, or it's not skewed. That's not enough to say skew. You need a gap. You need a gap to have skewness. Okay, somebody asked about the classes. Okay, so the classes, yes, there's 0, 0 to 0, 4, 0, 5 to 0, 9, 10 to 14, etc. 15 to 19. And the reason I do it like that is so that all the numbers have the same first digit, so they can share the stem in that class. And similarly, all the numbers have the same first digit, so they can share the stem in that class. Okay? And I guess my bottom got cut off, so let me shrink it a bit so you can see what I wrote. Let's do it like that. There you go. Okay, so take a snapshot if you want, or reproduce it, watch it later. So with the 5 features I go through in the solutions, I discuss systematically why Ruth is a better hitter, better baseball player, in other words. So questions? So I wanted to talk about that. Now let's look at the Newcomb data. This is the data set for all the data that I share with you. It's very blurry. I'm going to reboot it. But you should have that in front of you. If not, open that up. Again, this is the summary. Oh, just trying to make it bigger. There you go. All right, so you see the data set. These are the observations counted. This is Maris data, Ruth data, spending data, and then this data set, Newcomb's data. Now, Newcomb's data, I ranked it, I put it in order for you, and it represents nanoseconds. So what was done to measure the speed of light was flashed from a location higher at an altitude, down to a mirror where the reflection could be seen at the bottom of a mountain. I can't remember if it was where the Washington Monument was. Anyway, it went from a high altitude, light was flashed to the edge of a mountain, and it was measured down there the time that it was seen in the mirror, or where the reflection was observed. So the time was taken at the top altitude and by an assistant, and then the time was taken, the actual time was taken at the bottom of the mountain, and then the time it took, the difference in time was calculated, and that's what the data is. The data collected then was the time it took for light to pass that distance, to cross that distance. Now these are very, very small time intervals. So they're actually recorded in nanoseconds. And they were very similar. So most of them, as I explained somewhere up here, I explain here. Let's just read this so I get this straight. It says, and then again, I gotta shrink this a bit. Light travels fast, but not instantaneously. Over 100 years ago, Simon Newcomb in the US repeatedly measured the time in seconds that a light signal took to travel 7.4 kilometers from his lab to a mirror at the base of the Washington Monument. Washington Monument. I said Mount Rushmore, but that's not it. Okay. As a measure of the speed of light, he would then divide by 7.4 kilometers the approximate time it took to travel the distance. The speed of light will be measured then in kilometers per nanoseconds, where there are 10 to the 9 nanoseconds in a second. And the data down here, there's a note. It says, measures in the data are deviations from 24,800. So all the numbers you see in the data set are from 24,800. Okay, so this one was 24,816. This one was 24,816, 24,819. And these ones just are a little bit less than 24,000. So they're very close. But to actually make a graph, a chart and to analyze deviations or changes or differences, I need to look at the differences. So I'm just looking at these numbers. You see they're very, very similar. So I have a total of 66 observations for Newcomb's data. When you have more than 50 observations, we move into a different kind of a graph. We decide to use a histogram. So what I did here was I had plotted as a stem and leaf. It looks really skewed, right? Because look how many observations are here and here with just a few around it. But then there's just these over here. So these are clearly outliers. Even if I tested them, I'd find they were outliers. So as I explained, we should use a histogram instead. We're gonna cover how to make a histogram, unless you saw it in a video. Did anybody watch a video of me making a histogram? Because I was looking through it and I didn't see that I did teach that in the videos. So I want to make one now. So the question is, did anyone see me make a video on histograms? Drawing a histogram. Oh, well, this is not going to be that long, but was it using this data, Eliana? The Newcomb data? Sorry, I have to ask. I apologize. I was looking for it and I couldn't find. Okay, so let's just do it for people because nobody else is responding to my question. So I'm going to do it. I think it's worth it. And we'll have it here. Oh yeah, that's it there. That's it. Page 20, frequency relevant, 15 minutes. All right, so I'm going to tell you guys to watch that then. It'll be just as good there. So I explain how to divide up in video 9, how to divide up the data and set it up for the histogram. And then I explain the relative frequency histogram. So what I want to say here is these observations out here in the tail, whenever we have outliers, we need to investigate them, right? Similarly, I didn't talk about it, but up here, when we saw Maris and Ruth's data, or if I put back the stem and leaf drawing, this curious outlier out here needs to be investigated, doesn't it? How is it that in one season he did so well when most of his observations are over here? This is worthy of investigation. Now in the baseball league, anyone who follows baseball or sports, you're aware that they do not allow athletes, the players, to use human growth hormone or steroids to enhance their performance. It's just seen as unfair. But regardless, some do anyways. So this would be something that would be worth investigating. But obviously, if they didn't do it then, we won't be able to know. But at the time, this would have been worthy of investigation because this was set apart from the other seasons up here. Okay, so similarly, we need to investigate what happened over here. Why are there observations that are way off the rest of the data? So I make a point in these notes to explain that even though you have all of the data in order, numerical order here, this data set, what I suggest is let's look at the observations in order they were recorded. When you look at that, here is the time plot. So this is another kind of plot of data you can have. Here is the time plot of the data. And what does it tell you? How can you explain? How does it help you explain what happened to the data? So you have order of measurement on the horizontal axis. So this is the first to the last observations from left to right. And here is our variable time on the vertical axis. So what do you say about this time plot? What do you think? What does it tell you? Nobody? Well, this is not, okay, well, Fabiola is clustered. Well, most of the observations are around 20, between 20 and 40. Okay, so most of them are between, it's very stable between 20 and 40, except for those observations of -44 and -2. But after -2, it never happens again. The data remains pretty much between 20 and 40. So what can we say? How can we tell a story about why that happened? So Jasmine is saying these are two possible outliers that occurred at the beginning of the experiment as a result of the researchers familiarizing themselves with the technique. So early on, they made some mistakes. They were trying to get into the flow of their work. They made a mistake. They miscalibrated, or they wrote something down wrong, or they just made a mistake early on, and they never made it again. So we refer to that as a measurement error, likely a measurement error. There are different kinds of error, or there's different kinds of outliers, or outliers result because of different sorts of reasons, and one could be measurement error. In that case, you try and correct it. If you can't correct it, you have to just discard that observation. So you shouldn't be discarding outliers without a rationale. I think the rationale for this case is pretty sound. And you would simply say, all I want to do is start a new page. Can I just go? Okay, there you go. So you could have outliers caused by measurement error. That says measurement. So that's actually, you measured it wrong. They measured it wrong. They wrote, if they measured it fine, but then wrote it down wrong, that could be called a data entry error. That's different. That's something else. That can be corrected if you have the original documents where numbers were written and then the transcription into another document, into a book or to be shared with somebody, and it was transcribed wrong. That would be a data entry error. In both of these cases, we would either try and correct or discard the data. But you have to keep a record of everything you do with regard to discarding data, why you did it. It has to be transparent. The third source of outlier could be simply what I refer to as a paradigm shift. Maybe it occurred that things actually were different. And you don't want to throw out that data because it's telling you something. You want to investigate further. You want to look for other variables that you missed that were affecting, you weren't able to control to conduct the experiment, for instance. Okay, so the classic case of let's say, of miscalculating or incorrectly discarding outliers is the case of the Challenger, the space shuttle that went up in the 80s that exploded. That was later attributed to the panels on the shuttle that were in experiments. They were not they were incinerated, but they were breaking down at an altitude or under certain pressure that the researchers didn't understand. They just threw out that data because they couldn't explain it, as opposed to studying those parameters differently, like looking deeper at the rationale. Anyway, so that's a classic example of a bad decision in terms of discarding outliers. So you need to investigate when things look completely different, determine if there are different circumstances causing different conditions or variables that are affecting your results or determining your results. Okay. Oh, that says discard. I'm sorry, it's just so hard to write on this thing. Discard. Throw away. Okay. So outliers could be caused by measurement error, data entry error, or paradigm shift. In the case of paradigm shift, you're going to have to look deeper. Don't throw anything away. Okay, so if you throw out those observations, you end up with this. If you throw out those observations for new comms data, you end up with a nice symmetric predictable, reliable distribution where most of the observations are between 25 and 30. Okay? So a histogram is used when data are, when there's lots of observations. And here's the question now for you. What is the main difference between a histogram and a stem and leaf plot? Right, so the main difference, Jasmine, is that the stem and leaf shows the actual values, that you can see them. The histogram groups together the values within a class. You don't actually see the observations. The pattern, the overall pattern of a histogram or of a stem and leaf plot should be the same, but the histogram, you lose the actual values. Yeah, that's a way to say it, Raphael. Histogram focuses on frequency. It's not frequency of observations in an interval. It's not, you're not going to see the actual numbers. So the difference between histogram and stem and leaf plot in the stem and leaf, you can actually see all the observations, but in a histogram, there's so many observations, it'll just be, it's an eyesore. It's messy to throw all the data together in a stem and leaf plot. Instead, we use the histogram to display the pattern of the distribution. I'm going to be more clear. You see all the values of the observations. The numbers are in the stem and leaf plot. So there's two different kinds of histograms, and again, if you haven't watched that video number 9, Ileana posted. Watch all the videos. It's assumed you're watching them, so you need to see them. So see video 9 on stem and leaf plots, and you're going to learn the difference between frequency histogram and relative frequency histogram. What's the difference? What's the difference and what is the similarity between those two? Okay, Hector laid it out for you, okay? So the frequency count, so one is the frequency count and the other, okay, which one is which, right? So for the frequency histogram, whatever your observation, whatever your variable is, the values for the variable will go here in intervals. And for a frequency histogram, you have the number of observations, the frequency counted, that makes the height of the bar. In the relative frequency histogram, you notice you don't see the numbers, they're just all grouped together. You just know the interval they fall into. For the relative frequency one, the vertical axis is the percentage of observations. It's going to look, the numbers will be slightly different. So it's a percent of observations of the total. So it's going to look, the scale might be different, but the pattern will look the same. Depends on your scale and how you drew it, but it should be the same pattern, okay, as before. And when I say same pattern, what I mean are the same 5 features. So I've discussed what's the same, what's different, and now because they're different, you have to choose one. So which one do we choose? Which one do we use more in statistics? So which one do we use more in statistics? Yeah, just go ahead and guess. Let's see you guys guess. So I've said this before, I think. Statistics is about averages and relative measures. So now, what will you tell me? Which one do we use? Relative measures provide more information because in an instant, I will know what percentage of observations lie between certain values. Okay, and every histogram that's relative frequency histogram that I look at, if I was to smooth out the graph, what would be the area under the graph? What would be the area under the curve? What would be the area under the curve? No one? Ah, but the total number. What would be the value, Hector? Yes, refresh your page. So what would be the value under the curve? So let's say there was a total in this problem, n was 50, and there was 25, say 25 here, and 20 here, and 20 here, and how much is that? And then 35 here. Well, that doesn't make sense, does it? My drawings are off. Let's make it 20. I have to draw some more here. So we'll say 35. I'm going to do this again. I'm just doing this. 35, 30, and 30. And then this would be 5. Okay, so those would be how many observations fell in those intervals. But over here, I would have the percentages. So how many would be in the first? that would be 60%. Oh, I did this all wrong. This adds up to 100. See how I did that? Ah, you guys, I'm sorry. I was making them add to 100. Okay, so let's say they totaled 100, but that's not making my point because then they're both going to total 100. Okay, let me do this again. My apologies. See, this is why my edited videos are always better. So I want them to add up to 50. So let's say, sorry for the confusion. So let's say this is 20 here. I'll make this. So this is 15, this is 15, and this is let's say this is 18 and this is 2. So this is the number of observations in each interval. That's 18. All right, so that's how the observations, but under this, sorry, in the relative frequency histogram, if n was 50, the drawing, this would be 30%. This one would also be 30%. This would be 36%. And this would be 4%. Could you guys see that? So those are the percentage representations, and always under the curve you will have 100%, always. So going from relative frequency to relative frequency histogram is easier to compare distributions because you're always looking at 100% in the bars. Okay? It will always be 100%. With that, you should work through the normal distribution videos and exercises. What I'm going to do right now is jump to the end, because I did a bunch of videos and I explained things. But what I'm going to do is jump to the end where you don't have videos and work through those problems. And in the process, people who haven't reviewed the videos will gather something from it, and people who have already seen it will see this as a review. Okay, so that's what I'm going to do for 45 minutes. Unfortunately, I have to show you the question separate from solving it, because I destroyed my software. So maybe if I use the PDF version, I can make, no, I'm still gonna have to draw. Let's see. So I want you to go all the way to here and just finding the page. Okay, I want to start with the basketball example. On page 19, okay, see if you can find that on page 19. Okay, so Michael. So funny. Michael Jordan's height is 78 inches, whereas men have an average height of 69 inches and a standard deviation of 2.8. Rebecca Lobo, she's a female basketball athlete. Her height is 76 inches, whereas women have an average of 63.6 inches in height with a standard deviation of 2.5. Relatively speaking, who is the taller person? So how do you do this? So my videos stop at page 17. That's why I'm doing this. So how would we view how we compare these two people from two different populations? Right, so what we need to do is come up with a measure from what we've been given. We are going to convert or transform inches into the units of standard deviations from the mean. So we're going to assume, by doing this, we're going to assume that heights are normally distributed, or let's say not normal. We're assuming that heights are symmetric. Okay, we're going to assume heights are symmetric, and so we're going to convert height into standard deviations from their mean. That's what our approach is, and we're going to do it for both athletes and then compare them. So, right, Hector, you got it. So for Michael Jordan, for both of them, I'm going to transform the measure into Z. Z is the standard, a measure of units of standard deviations from the mean. To do that, I need to subtract by the mean, so I need to take my observation, which I'm going to call X. I'm going to subtract by the mean, and then I'm going to divide, I'm going to group it into standard deviations. So how many standard deviations from the mean is that observation for Michael Jordan? The Z for Michael Jordan is equal to 78 minus 69 divided by 2.8. And what do you get? Do the same thing for Rebecca Lobo. She's 76 minus 63.9. You should already feel where this is going, because she's almost as tall as him, but she's a girl, a woman. Okay, so 76 minus 63.9. Oh, sorry, I wrote it wrong. 63.6 divided by 2.5. So make those calculations. And the assumption is heights are symmetric. And then to do anything else with this about regarding estimation or prediction, you would have to assume they're normally distributed. For now, I use the symmetry to reduce this to Z. Well, Z is implying it's standard normal, so I guess I have to assume, and I'll say standard or normal, because I'm using Z. So the normal distribution is a special distribution that we use for predictions. And lots of data sets in nature, heights, weights, tend to have a normal distribution. And I even mentioned in finance, stock market returns tend to have a normal distribution, roughly normal. And what is normal? Normal is where they're symmetrically, the data is symmetrically distributed. Most of the observations are one standard deviation from the mean. 68% to be precise. And then for 2 standard deviations from the mean, I find 95% of the observations. And at 3 standard deviations from the mean, I find almost all of it, 99.7, which leaves outliers, okay? Because there's 0.3% are outliers. But I don't have to use any of that information for this problem. All I had to do was standardize. That's it. That's all I wanted you to do. So what did you get? So 3.21 for Michael Jordan, and look at that, 4.96. So it means for symmetric data, remember, for symmetric data, 3 standard deviations and beyond are considered outliers. So he's an outlier, and she's at 4.96. She's even more of an outlier. But she is taller. Relatively speaking, she is taller. All right? So what did we do? This kind of a problem is I didn't solve for probability. I was just standardizing. So I just refer to this as like a general normal distribution problem. It's a general problem. Let's get into some of the probability questions. Even though he's taller, she's a taller person relative to her gender. All right, let me get back to the notes unless you have any questions. So there's your answer. Michael Jordan's height is 3.21 standard deviation above the mean for men, but Rebecca Lobo's height is 4.96 standard deviation above the mean for women. Rebecca's height is relatively greater among women than Michael Jordan's height among men. All right, let's do this one now. Yes, Eliana, if you want to get the percentage, you could, but that was not the question, okay? You could just use the standard normal table, and while in both cases they're both outliers, but I think the standard normal table goes to 3.21. I mean 3.5 almost. So you could find the one from Michael Jordan. And Rebecca Lobo, you just say that the chance of her being that tall would be 0 because she's so far an outlier. Yeah, that's all the question was, is who's taller. So to do that, you figure out who's relatively taller in terms of strangeness or bizarreness. being an outlier is what we want to find. To find if they're outliers, we use the standardization. Okay, so now, same sort of problem. I'm going to ask some different questions though. Who has the better score? So these are two students who have applied to get into college. One has submitted their SAT score and the others submitted their ACT score. So now administrators have to choose or rank students. Who's a better student? Again, refresh if it gets blurry. Okay, you did it. So Eleanor is 1.8. Same technique, right? And Gerald is 1.5. So for Eleanor, you take her score and standardize it, turning it into the number of standard deviations from the mean, which tells me how bizarre it is or how unusual it is, if it's unusual at all. And when you do this, you get 1.8. And Gerald you take his score and standardize it, and the formula for standardizing, if you don't know yet, is the value minus the mean divided by the standard deviation. When you do this, you get 1.5. So neither of them are outliers, right? This one is 1.8 standard deviations above her mean, and he's 1.5 standard deviation above his mean. So she is the better student. She has the better score. Now that's part one. In the second part, I ask for you to convert that to a percentile score. So what's a percentile? Percentile is its value tells you how what's the percentage of students in this case that did worse than Eleanor. So let's do second part for Eleanor, what we want to find out is what is the area to the left of 1.8? What's this? That is a percentile. Percentile is area to the left. If the percentage is on the left, the percentile is this value, but which percentile is it? In other words, what's the percentage on the left of it? So what you do to find this is you go to the tables, now I'm going to scroll through to find the tables for you. There they are. Okay, so we go, I explain how to use these tables. If there's anything missing in the notes, let me know. I mean, in the videos, let me know and I'll cover it. I think I covered most. One of the videos was defective at some point. So let me know if anything else goes defective that I have to replicate. So I'm looking for 1.8 as the Z. So that's not here, right? Because this is the negative. So I'm going to go, there, I passed it. 1.8, there we go. So that's exactly 1.8, so 96.41. Very good. So this is 96. 0.41%. So that means 96.41% of students did worse than her. So she's in the top. Another way to see this is that she's in the top what percentage? So she's in the top 3.59% of students. Yeah, almost like even tighter, even less than the top 5, right? To be precise, I got that by doing 100 minus 96.41. Okay. So she's in the top, she's the 96.41st percentile, or you could say she's in the top 3.59%. Now Gerald's not going to be as high as she is. He's going to be still high though. I'll draw Gerald. Oh, my niece is calling me. She decided to call me. All right. So 1.5 would be around the same place, but so 1.5 where does that put us? So we go back to our chart. And you see it's 93.32. So he's in the top 6.68%. All right. Okay, what's next in these questions? So all the other pages are solved. Just these ones that I'm doing now are not. If you want me to repeat something, let me know. Or clarify. Okay. So we already know Eleanor's score is better. She's a higher, more standard deviations from the mean than Gerald, and it's the same thing to say she's in the 96.41 percentile and he's in the 93. So he has 93.32% people worse than him. But what if now I ask the third question? What would Gerald have had to get to be in the 99th percentile? So now what we want to know is what would it have taken for a grade to be even higher, 99%. So far then, what we've learned how to do is to standardize and how to find a probability after standardizing. Now I want to, so basically I was finding a probability. That was my approach. Now I'm going to go backwards. I'm going to give you the probability or percentile, and you're going to tell me where is this person in terms of standard deviations from the mean. And then we're going to convert it to a score. That's how so everything backwards. We're going to go backwards. So I'm going to draw this backwards as well. So I'm going to draw this backwards. I'm going to show this is 3. And draw my curve. And I want to be where there's 99% on the left. So that's all of this is 0.9900. And the reason why I write 4 decimal places is because the table, inside the table, where the probabilities are 4 decimal places. So it reminds me to go inside the table to look for that number. Doing everything backwards, I'm going to find how far I am in standard deviations from the mean. So what I want you to do for this class is always draw these standard normal curves, okay? This is what I want you to do. So we do things backwards, like I said. We go to the tables and we look inside for that number, 0.9900. So I go to the tables and I look for that number. Now it's not here because these are the smaller than 50%. Now I'm going into the positives. I start looking for 0.9900. The closest I can get is between here and here, but the closest one is this one. And my rule is to go for the closest one. So the answer, unless it's perfectly in the middle of 2, but it's not. In this case, it's closer to 9901. So that's 2.33. Does everybody agree? So this is 2.33 standard deviations from the mean. Are we finished? Very Very good. Are we finished? We're not finished yet. This is Z, 2.33 standard deviations. But I want to know in terms of score, I want the answer in terms of X. I want it in terms of the units of grade. So what I want to do, where Z was X minus mu over sigma, this time I want to actually solve for X. Now you could just use this expression and put values in here because you have Z, you have mu, and you have sigma, and you can just solve for X. Or you can learn the other way to write this and say to yourself, algebraically and with reason, X is equal to Z standard deviations from the mean. So as I'm saying it, the symbols are appearing. So 2.3 Z standard deviations for Gerald, six plus the mean of 18 . And when you put it together, it's 31.98. Oops. Oh my goodness, I'm too close to the arrow. I'll go up. So his score would have had to be 31.98. Notice this formula is the same. So this is what I call the standardized formula . Is the same as, it's the same formula, but I refer to this form of it as unstandardized. You're turning it into the units of the problem. It's hard to write on this, sorry. Say it again. Unstandard eyes. Okay. So you undo it, you unravel it to get the score. Did you guys get the same as me? Right. And then I ask you, what would Eleanor have to get to be in the top 5 percentiles so she can get a smaller grade? You repeat the steps to solve that. Let's look at that from number 4. So what score would Eleanor have to be in the top 5 percentile? We draw things, we do them backwards. So again, I'm asking, when I give you a percentage and you have to find the score, you have to find the units, you go backwards. Okay, so that's my tip to you. So if you're given X and you're told that it's normal with a mean mu and a standard deviation sigma, you can find the probability. This you would do by standardizing. And I broke up this unit into basically 4 problems that you solve, and then just some other general type problems. So once you get the pattern, it's always the same thing. It's the same steps. You just have to know which one to do. So if you're trying to find the probability, you're going to have to standardize and use the table, right? If you're given a probability, and you're asked to find X, a value, the score on a test or the actual weight or sales or something like that, given probability, and you're asked, wow, I missed so many words here. If you're asked to find X, then this is when you do the backward problem and you have to unstandardize at the end. Okay, so let's continue with the backward problem and then go watch the debates. Let's see. So that's the backward problem again. We're going to repeat what we did. Eleanor, the top 5%. So for Eleanor to be in the top 5, Eleanor would have to be here. If it's 5% on this side, it's 95% on this side. So 9500, right? So the question is, where is she? How many standard deviations away is she to have 95% below her? So you're going to look inside the table for 95. And I'm looking for 95. And the closest I get, aha, is between these two. Evenly between these two is 95. So my answer is 1.655, I believe. No, 45. Okay, 1.645. Got it? So Z is equal to 1.645. And now you need to unstandardize that. Now I'm teaching you using these graphs so you really have a better sense of what's going on. However, if you do know what's going on, you can easily get the answer using Excel. And I do provide you the code for doing that. I can talk more about that next week. We can start with that and then I can solve problems in preparation for the test. But let me finish this first. So that's the first thing I do. Now I found the Z, but I need to convert that into X. So this converts by the formula X equals Z standard deviations from the mean. So Z is 1.645. Sigma for Eleanor go back. Sigma for Eleanor is 100. And plus the mean for Eleanor is 500. And when you put that all together, her score is 664. 6.5. How's that? To be in the 95th percentile. So what you should be doing is completing as many of these problems that you can. Let me know if you have questions. I provide you with all the solutions, I believe, for the homework and for these exercises that follow in the notes. Then you have the midterms. You can practice all those midterms that I gave you. Okay, so keep yourself organized, and next week I will answer your questions, or we'll solve midterms together. Okay, any other questions for now? Seriously, that's basically it. Some basic problems about normal distribution. There's probably like 3 or 4 that might stump you. Let me know. Contact me. Send me the problems, and I will either meet with you in a chat room, or maybe even by email. I can explain where you're going wrong. It's usually the same sort of problems. Thank you, Hector. Thanks for helping me out with the chat. Great, Eliana. Okay, so you have all the resources available to you. Don't go looking for more problems. Don't go look for more instruction. Just dedicate yourself to watching everything I've done, and then ask me. If you still need help, let me know. Okay, so you guys can go, and I'll stay on a couple of minutes to see if anyone else has any questions. So have a good night and have a good week, unless I hear from you. I will send an email to everyone to confirm that we will postpone the first test until October 1st for the first hour and a half of class. Good night, Jasmine. Thank you. Good night, Maria. Good night, Hector.
Good night, Edgar.